All right, welcome back. Dr. P here, and in this lecture we'll look at some different ways of preparing alkyl halides. In particular, we're going to look at radical halogenation of alkanes, and this is typically chlorine or bromine. Iodine just doesn't react fast enough, and fluorine reacts too vigorously to really control. So you usually end up, if you try to fluorinate something via radical fluorination, you end up polyfluorinating it. Fluorine goes everywhere. And often we only want to put one halogen on a molecule. We'll also look at allylic bromination. And that's using a reagent called NBS, N-bromosuccinimide, and we'll talk about that in just a little bit. And then lastly, we'll look at how we would prepare, we can prepare alkyl halides directly from alcohols. Now, when we get into chapter 11 in some more detail, we'll look at substitution reactions, and if we use certain halogens as nucleophiles, we can do a substitution reaction to prepare our alkyl halides. And preparation from alcohols is a form of that. Okay, so let's take a look at the radical chlorination of methane. And I can't remember if we've gone over this or not, but I think I did way back in chapter 2. So just a bit of a review. We'll use chlorine and some kind of light. That's this H nu here. And that will give us CH3Cl plus HCl. That can keep reacting. And we'll get CH2Cl2, methylene chloride, plus HCl. That can keep reacting, and we'll get CHCl3, chloroform, plus HCl, and that can keep reacting, and we would get CCl4, carbon tetrachloride, plus HCl. So an important thing to note here is that chlorination is not very selective. And in the text, there is a little description, I think, of the relative selectivity of chlorine versus, say, bromine. I can't remember if it's in the text itself or if it's in one of the, maybe one of the end of chapter problems. But the take-home message is that chlorination is not very selective. And, you know, so we could look at, for example, the chlorination of propane. And I'm going to draw out all of my H's here because, you know, if you have something like methane or ethane, all of the hydrogens are the same. But in propane, these hydrogens attached to the middle carbon are different than the hydrogens attached to the end carbon. We'd see them in a different place in NMR, for example. So if we were able to add just one chlorine, we would actually get a combination of products here. Okay, so notice that we could have the chlorine added in place of one of the end hydrogens, which I'll label here as A, or let's see here, where's my blue pen go? I've lost my blue pen. Oh, there it is. There's my blue pen. Or we could have HB, and if we swap one of those, we end up getting the chlorine on the middle. So there are some interesting features about this. Now let's take a look. We've got 1, 2, 3, 4, 5, 6 HAs and 2 HBs, which would mean we would expect a product ratio of 6 to 2 or 3 to 1. We should have 3 times as much of this as we do of this. But it turns out that that's not the case. We actually get it's something more like I think it's more like a 30-70 mixture. Hold on a sec here, let me just check here. I have to do a real quick calculation. Give me one sec here. Okay, it's about a 50-50, I think. I think it's about a 50%, 50-50 mixture. I'm not sure. I just did a real quick estimate. So that's interesting. So what this tells us is that the intermediate that gives us our 1-chloropropane is not as stable as the intermediate that gives us our 2-chloropropane, because we've got way more 2-chloropropane than could be accounted for just by the number of possible hydrogens at position B that we could substitute. So let's take a look at that step in the intermediate. And you can go back and check in chapter 6. I talked about initiation, propagation, etc. But one of the intermediate steps in the mechanism and let me just put this back up here. One of the intermediate steps involves HCCCH, and then we've got our plus Cl dot. So our initiation, in the initiation step, the chlorine falls apart to give us 2 chloride radicals. And then we could get now chlorine, it's supposed to be an arrow. And that's going to give us, let me draw in the equilibrium arrow there. Excuse me. And that's going to give us now do it in black here just because I think it's a little easier to see. But I'll draw this guy in purple. So this is our primary radical. And if the chlorine instead reacts with the hydrogen, one of the hydrogens on the middle, then we'll get a secondary radical. And now these radicals follow a certain trend in stability that is actually the same as carbocations. So the more substituted we have our radical, the more stable it would be. So a secondary radical is more stable than a primary radical. And depending on what halogen we use, this difference can make a big difference, like with bromine, or a small difference, like in chlorine. So for example, I should mention that radicals can also be resonance stabilized. So we can look at the radical bromination of propane, and we'll see the following. We'll have our propane, and we'll go ahead and use Br2 and irradiate with the correct frequency of light, and we will get some 1-bromopropane plus some 2-bromopropane, just like we got 1-chloropropane and 2-chloropropane. Sorry, spacing out there for a minute. And now we have a product ratio of around 3%, 1-bromo and 97% 2-bromo. So what we would say then is that bromine is much more selective. Okay, chlorination is not very selective, but we'd say bromination is selective. So that's often why you'll see me, like in doing a synthesis, using something that has bromine in it. So stick a bromine on something, because you could, and you can use this in synthesis. So let's say this may be a way to make a an alkyl halide easily from just a plain alkane. So you don't have to have the alkene in order to add Br to it. You could add bromine to the middle one if you already had the alkane. Now let's say, however, that you wanted to do the following. Let's say you wanted to do what we call allylic bromination. What is allylic bromination? Well, allylic bromination is doing the following. we will stick a bromine and just one bromine at that carbon in the, we call that the allylic position. So it's 1 over from the double bond. Now the reason that we do this is, or rather the reason we do this the way we do, I'm going to just cut to the chase here and say use NBS. So we'll use here NBS, sometimes written as Br2 and NBS. But typically I'll just write NBS. NBS. See, the problem is if we try to do this, what we'll get is the bromine will simply add across the double bond, and so we don't want that. That is not so good. Okay, so we need to have a little bit more control. So by using NBS, we control the amount of Br2 that's actually there. In fact, there's no Br2 there. So NBS, which stands for N-bromosuccinimide, NBS equals and essentially what happens is this nitrogen-bromine bond falls apart, and this gives a bromine radical, a bromide radical, without any Br2 present. So we keep our bromine concentration low, so we avoid this reaction, and instead we will selectively brominate just at the allylic position. This also works for the benzylic position. And we can go ahead and use NBS to stick a bromine right on that benzylic position. All right. Now, the last thing to talk about is from alcohols. So preparation of alkyl halides from alcohols. And so typically what we'll do here is we'll use, there's sort of two different ways that we can do this. One is via an SN1 substitution. And for example, and I won't write it out because you guys should have this in your notes, synthesis of T-pentyl, not pentyl, pentyl chloride. Lab. Okay, you did an SN1 substitution. But we can also have some substitution using other reagents. Okay, SN1 is really best for works for tertiary, whereas substituting using other reagents works for primary or secondary. So if you had a tertiary alcohol, you could do an SN1. If you have a primary or secondary alcohol, SN1 really isn't going to work that well because the carbocation intermediate won't be that stable. So what you're going to have to do is use a little bit more vigorous reagent here, and typically what we'll do is we'll use something like, let's see here. OH, so Cl2, we'll get Cl. We'll also get plus SO2 plus HCl. And then we could also do something like PBr3, which gives us bromine there. Okay, and typically that now gives us, what's my other, H3PO3, phosphorus acid. Other reagents that could work, let's see, I think PCl5 works. I think PBr5 works as well. PCl3 maybe, but these are typically SOCl2, which is thionyl chloride, and let me just write that here, SOCl2 equals thionyl chloride. Why am I telling you that? Because you might run into it. Well, hopefully you don't run into some thionyl chloride in a dark alley or something, but you might see a bottle of it in the lab next semester. All right, so we can directly make our primary or secondary alkyl halide, and I just drew the secondary here, but it works for primary as well. We can directly make these from alcohols using thionyl chloride to get the chlorine, to get the chloride, and PBr3 to get the bromide. All right, so that wraps up ways of preparing alkyl halides. These are good things to know for synthesis. And in the next video, I'll talk about reactions of alkyl halides. So until next time, stay safe. Bye now.